Holding product's not working on the process, right? So control is a lot stronger than monitoring. And of course, devote your resources to where they count. Now, another issue, specifications, managing specifications. Ideally, specifications would be set for product performance, right, in the design of the product, right? Design it for end uses for the customer, potential end uses for the customer, and they'd remain that way for the life of the product. Well, that's not reality, right? Reality is that they change, right? There's new markets that develop. People want to have maybe product that meets tighter specs, things like that, right? So they change over time, right? Product and process design groups often own specifications. And usually, in most organizations, manufacturing groups are responsible for things like cycle time, throughput, yield, things like that. Well, one organization, the thinking became that, well, let's make the process and product design groups responsible for yield. Well, you know, they said, why should manufacturing have to be responsible for a low-yielding product when the design stinks, right? You know, and you give the product design people more ownership over the process once it's in manufacturing, so they just don't throw something over the wall, right? Heard that expression, right? Manufacturing, so kind of makes some sense. All right, so design groups have that responsibility for yield now. They start looking at some data, right? And they start seeing some interesting things, right? They look at its critical parameter, look at lot average, right? And they find out, oh, in this tail, these 4 of these 7 lots out here had low yield. We can address that, right? Since we have control over the specs, we'll set the specs there, all right? Set the specs so that those lots out there, they don't meet spec anymore, right? Okay. Well, eventually a customer came in, requested an audit of an operation, and said, I want some CPK values. They made it clear these would be to calculate on individual product units. Now, the specifications have been set using lot average results, right? They produced CPK values that were, you know, still not very good, right? 0.8 or so, not so hot, right? However, we can't do that. We can't do that because those are on lot averages, right? We're going to do them on individual measurements. Oh, no, okay? Now the CPK drops to 0.38, half, right? So what happened? Right? Well, this company clearly forgot about the central limit theorem. Average is very less than individual results. Right? Most important theorem in statistics. Right? We wouldn't have, statistics wouldn't be involved at all in manufacturing, I don't think, without the central limit theorem. Okay? Or in much of life, actually. They forgot about that. What they were doing is they were using specifications as disposition limits, and they did not realize the difference between disposition limits and specs. They're different. So, understand your limits. Specifications apply to measurement results on individual product units. Ideally, those specifications are set by product design to ensure functionality for the end use that's intended or imaginable. They're used with customers and management, right? Reporting metrics such as CPK, talking with customers about what the product unit's going to do for them, right? They're really not of much direct value to manufacturing. Day to day, they don't really need to know, they don't really need to have the specs. Right? Product unit results are going to have the widest distribution, so they're going to have the widest limits. Disposition limits, they apply to a statistical summary statistic collected during production of the operations, right? Something like a lot average. Right? They're used for disposition of product. Right? Product control, scrap, rework, hold for some kind of evaluation. Right? They apply to a finite amount of product. Right? Maybe since the last observation that you got, right? The product in that group is now come into question because you got something outside the disposition limit. How do you set them? You set them, there's classical ways to do it, minimize customer and producer loss. Summary statistics are generally going to have narrower distributions than product unit results, so they're going to have narrower limits than specs. And there's these things called control limits, right? Control limits also apply to some kind of statistical summary of the data, right? As collected during operations, like a lot average, or a run of lot averages if you're doing a run rule, or a group of past lot averages if you're doing something like a QSUM or an EWMA. These are used for process control, different than product control. Process control, you're actually going to do something different. Here you're going to worry about the product. What are you going to do with the product? That's the question you have to answer. Here, what are you going to do with the process? Right? Are you going to adjust it? Are you going to shut it down and look for an assignable cost? What are you going to do to the process? The product that's affected is potentially product from when you shut it down to the, and change something into the future, foreseeable future. It's indeterminate. Right? Back here, the product's finite. Right? Usually how we're going to set these, you want to balance fault signals with sensitivity, right? Using average run length curves will help. And ideally, you want to separate these as much as possible from your disposition limits and the related procedures. You want to try to separate control from disposition. They're not the same thing. Okay? Well, if you have the same statistic for each one of them, right? If we use the lot average here and the lot average here, that's going to confuse things to some extent. So maybe we need to think about using something different for each of these for our decision making. Okay, so what about process variation? Well, that's a reasonable question, right? Most SBC courses suggest addressing it by using R or S charts in conjunction with the traditional X bar. And so the purpose of this R or S bar chart is to exercise control over the within group variation. Right? These are calculated on within group estimates of variation, while the X bar chart's trying to control the process mean level. Right? These charts are also simple, right? Just a time sequence of the R or S values for each group, and usually they have an upper bound below which the value should be. Okay? So here's an example of wafer oxide thickness. Okay? This is some of the data. Okay? It's a single chamber, single etch chamber, finite time period. I think it was about 2 weeks. 50 wafers were involved. 5 measurements per wafer. Right? Measurements per wafer were done in a fixed sampling scheme. Top left, center right, flat. Okay? So you can see how old this data is. The X-bar chart was, control limits were set at the target plus or minus 3 times the standard deviation of the wafer averages. Well, you can argue that maybe that's not the best setting because it looks like there's maybe an assignable cause in here, right? That's not really what I'm concerned about, though. The S chart was set with a common approach where you take the average of the within group standard deviations and you multiply it by this V4 constant, right? Well, that turns out to be 27.4, right here. And it plots it up here. And here's the data. Does that look right? I don't know. Yeah, you got all your data down here, and you got a limit up here. All your data is maybe no bigger than 15 or so, and your limit's at 27. Well, it's not right. The problem with this S chart is that it doesn't conform to the assumptions behind building an S chart, calculation of the limit. It's not so much the normality assumption, but the assumption that the within group variance is a single variance component. That's all it is. It's just a single variance component. That's the model that it assumes. For this data, there happens to be a fixed systematic profile present across the wafer. Looks like this. Okay? It's a bowl shape. Okay? The center's low by about 20 angstroms. The left and right are high by about 10, and the top and the flat are about at the average. Okay? So you got a bowl shape. And it's fixed. And it's really obviously present. Okay. Now, combined with the fixed sampling plan, it means we're sampling all of these different points each